then we're going to revisit this. At that point, our confusions must be eliminated. That's going to be the goal. Okay. So I'm going to close this question in 5, 4, 3, 2, and 1. And here are our responses. Okay. So we have selected, one answer from all the choices. One of them is correct. Okay. Which one is correct? We are going to get to that in about 10 minutes. Okay. Now, just to recapitulate what we have done on last Thursday, we talked about the covalent bond, and then we talked about how the energy is released during the covalent bond formation and how it brings down the potential energy. Okay, because strong attraction, less repulsions, and also it's gonna bring down the kinetic energy, more space, electrons slow down. Okay, so total energy is decreased, therefore energy is released during bond formation, and the opposite is true during bond breaking. And you will be tested on that. That exact thing that we just discussed, that I just told you on your exam to be as well. So, if you understand that, that would be wonderful. You're going to score points because of that information, okay? Anyway, and then we talk about how bonds are held together by bonding electrons, okay? What is in between the two repellent nuclei are electrons. And the thing about the electrons is these electrons move around constantly, okay, in random directions. As a result of that, this bond is not going to be static. It's going to be dynamic, meaning the bond is vibrating all the time. Okay, and if something is vibrating, we can define what we call the vibration frequency. And then what we know is, what we discussed towards the end on Thursday was this vibration frequency is directly proportional to the bond strength, and then inversely proportional to the masses of the atoms involved. Okay, as we can, as compared to a spring, right? It's comparable to a spring. So that is what we have talked about so far. Now what we're going to do is we're going to get into the IR spectra and then make sure that we understand this thoroughly, okay? So let's think about the IR spectrum that you were looking at before. Okay? Even this IR spectrum, okay? You can see in the IR spectrum, unlike other absorption spectra we have seen, the x-axis is not wavelength. It is wave number. And what is wave number? Wave number is the inverse of the wavelength. It is important that we understand the distinction here. I'm going to write this down. This is the wave number. And wave number is, I'm going to give it the Greek letter nu with a hat. We call them tilde. Nu tilde, okay, is equal to 1 over wavelength. Okay. This much we need to know. Wave number means 1 over wavelength. That is it. Okay. They could have easily used wavelength there. Instead, the IR spectroscopists decided to go with wave number. Okay. They are weird, but we have to roll with them. All right. Anyway, and also another thing is that we can appreciate the absorption spectrum is not in the absorbance mode. Okay, we have upside down peaks, meaning what we have here is the transmittance mode. Okay, so when the sample absorbs light, we're going to have dips in the transmittance. That's the idea there. All right, and those are the weird things about the IR spectra. And then the other thing is, I'm going to stop talking in a bit. Just bear with me for like 2 more minutes. Now, we understand this relationship. Wave number is 1 over wavelength. And also, I want to remind you that energy is equal to what? Energy of a photon is what? What is energy of a photon is equal to? Lucas? Perfect. Thank you. Planck's constant times the speed of light over the wavelength. I'm gonna say Planck constant times the speed of light multiplied by 1 over wavelength. Okay. So we know 1 over wavelength is the wave number. Just like this, right? Wave number, meaning we can rewrite this energy is equal to hc times the wave number, or it doesn't matter, this equation doesn't matter that much, but the relationship matters. Okay, what this tells us is energy is directly proportional to the wave number. Higher the wave number, higher the energy. Just like the frequency. Higher the frequency, higher the energy. Just like that, higher the wave number, higher the energy. This is something that we can actually quickly derive from this. Okay, at this point, what questions, concerns, comments do we have? Anything? Okay, so what we have done so far is we have looked at an IR spectrum. We have appreciated that the IR spectrum x-axis is not wavelength, is wave number, and it is in the transmittance mode. Okay. We noticed that about IR spectra, and also the wave number is 1 over wavelength, and then the energy and the wave number are directly proportional to each other, and that is all that we have discussed so far. Just to summarize at this point. Any questions, concerns, comments? Okay. Now I know that I talked a lot, maybe a lot, not maybe just a few minutes. And what I'm gonna do is I'm gonna go back. Okay. Now this slide shows different modes of vibration of the bonds. Okay. Bond vibrations can be symmetric. Okay. Just like that, or anti-symmetric. So symmetric is like this. Okay, it goes like that. Okay, anti-symmetric means goes like this. Okay, and can be scissoring like this, or it can be rocking. It's like a concert, right? Okay, so they're like molecules. Let's see, molecules are constant. Anyway, the idea is this: we know vibrational motions of the molecules are induced by what radiation? Vibrations are induced by what radiation? What's that? Infrared, right? Therefore, what we're going to do is we're going to be using infrared spectroscopy or infrared radiation to induce transitions between vibrational states in molecules. Okay, so that's the idea behind using IR spectroscopy to identify the bonds. Okay, so when we expose this to infrared radiation, it goes from one vibrational state to another vibrational state. Okay, and then here's a IR spectrum. Now I want you to make a note here very clearly. Okay, this is the first time actually I asked you to make a note, so it's important. Okay, IR spectrum tells you what bonds we have in a molecule. Very simple. Period. IR spectrum tells you what bonds we have in a molecule. That is it. For an example, by looking at this IR spectrum, we know we have C double bond O, and then we have CH bonds just by looking at this. That's all I know from this IR spectrum. Okay, why this is the case? Each of these bonds have their unique bond strengths and the masses of the atoms involved, meaning the wave number or the IR wavelength or the wave number they used is going to be unique to that given bond. Okay, so for example, if you see a peak at 1750 per centimeters, then that must be a C double bond O bond. Okay, and then for different CH stretchings, you have different wave numbers as well. So if you can memorize these wave numbers and then what bonds they are associated with, then we can determine the bonds in any given molecule. But here's the thing: you don't have to memorize. Okay, whenever I give you an IR spectrum, I'll give you what bonds we have according to the IR spectrum. Okay, so you're welcome. Anyway, so only thing you have to do is build the molecule from there. All right. Any questions, concerns, comments at this point? All right. If you don't have questions, I will have a question myself. Okay. Here we go. Now let's try discussion. Go ahead. Oh. Answers. All right. We have more than 90% responses now. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are our responses. Okay. Yeah. So we are mainly between CEO and the OA stretching, but most of us selected CEO stretching, and that is the correct answer as well. Okay. Now, why this is the case? Anybody who wants to tell me why this is the case? I know everybody wants to do this, but anybody? I have a hand there. Thank you. Remind me names one more time. Zach, go ahead.
The CO stretching has the lowest wave number, which is proportional to the energy.
Thank you. That is it. Yeah. So CO stretching has the lowest wave number. We know energy is directly proportional to the wave number, right? Lower the wave number, lower the energy of that photon. So CO stretching requires the lowest energy photon out of the peaks given to you here. On the other hand, OH stretching has a higher wave number, requires a higher wave number IR radiation. Therefore, it requires the most the photons with the highest energy to induce OH stretching vibrations. That is it. All right. What questions, concerns, comments do we have at this point? Anything? Any questions, concerns, comments? I know some of us flip this, but remember the relationship energy is directly proportional to the wave number. Higher wave number means higher energy. Okay. So just like frequency, higher frequency means higher energy. Just like that, higher wave number means higher energy. All right. Any questions at this point? Now let's do this. I'll reopen the question in case somebody wants to revise the answers. Only revise the answers if you understand it. If not, think about it. And when I reopen it this after class, you can get another chance to revise the answers at that point. All right, let's do this now. We know CO has the lowest energy. What is it? Can you calculate the energy? Go ahead. All right, I'm going to close this question in 5, 4, 3, 2, and 1. There's 75% responses almost. Okay. Oh, more than that. All right. Now, before I look at the answers, I'll show you the way I would handle this, okay? So that we don't have to think too much. So this is all about the understanding rather than, thinking. And the problem here is not, if it is hard, if it's not hard because of chemistry, it's hard because of some math issues like having to do with conversions. All right, here's how it goes. We know we are given the wave number, which is 1 over wavelength. Okay, 1 over wavelength is 1000, right? 10 to the power of 3 per centimeters. I made 1000 10 to the power of 3 because 10 times 10 times 10 is 1000. Okay. Anyway, if we know the wave number, then if we take the inverse of this, we can find the wavelength. So the wavelength is 1 over 10 to the power of 3 centimeters. If we take the inverse of per centimeters, it's going to become centimeters. That's what I did there. Okay. So this is the wavelength now in centimeters, but we don't want that in centimeters. We want that in meters. So what I'm going to do is I'm going to multiply this by 10 to the power of -2. Why? That's how many meters we have in a centimeter. So if I do that, centimeters cancel out, and then we're going to get the answer for the wavelength in meters to be 10 to the power of -5 meters. Done. Okay. And then we know our equation to calculate the energy is E is equal to Hc over lambda. H is 6.626 times 10 to the power of negative 34 joules seconds, and C is 3 times 10 to the power of 8 meters per second, and divide this by the wavelength, which is 10 to the power of negative 5 meters. Okay, now we just need to plug these numbers into a calculator and then crunch them. Okay, so when you do that, make sure that you open parentheses for all the numbers to include all the numbers in the numerator, and have a parenthesis here as well. It won't hurt if you have parentheses. You will get used to it. Okay, anyway, this is for you. I don't have a calculator, so I'm going to try to do this manually. So I can cancel out 10 to the power of negative 5 with this, and then this should be 10 to the power of negative 21. So I get 3 times 6.626, which is like 19.8 times 10 to the power of negative 21. And I see that my meters cancel out, seconds cancel out. I'm going to get the answer in joules. And this is equal to 1.98 times 10 to the power of negative 20 joules. And that should be the energy of my photon in joules. But I want this in kilojoules per mole as well. So what do? This is one answer, one of the answers. And to make this kilojoules per mole, I take this number, 1.98 into the power of negative 20 joules, and multiply this by the Avogadro's number, 6.022 times 10 to the power of 23. Why? That's how many photons I have in a mole of photons. And divide this by 1000, which is how many joules we have in a kilojoule. And it seems like, oh, this is nice. And this is 20. This cancels out. I'm going to get something like 12. 12 kilojoules per mole as the answer for kilojoules per mole. That's it. All right. I'll give you 30 seconds to think about this. Talk with your neighbors, do a gut check. And if you have any questions, I'll answer any questions you might have. All right. What questions, concerns, comments do we have? Any questions, concerns? Yes. Carlos, can I have the microphone with Camilla, please? Camilla, go ahead. Thank you for your question, by the way, Camilla.
How did you get the 10 to the negative 5 again? Just
10 to the negative.
the negative 5.
Keep the microphone with Camilla, okay? So the wave number is 10 to the power of 3, right, Camilla?
Yeah.
Okay. If you take the inverse of that, that's going to become 10 to the power of negative 3 or 1 over 10 to the power of 3, correct?
Yes.
Okay. And then to make it meters, I multiply by 10 to the power of negative 2 because that's how many meters we have in centimeter. Are you with me so far?
Yes.
And then when you multiply 10 to the power of negative 3 or 1 over 10 to the power of 3 by 10 to the power of negative 2, you get 10 to the power of negative 5, yes?
Yeah. Okay. Thank you.
Yeah. Do it in your calculator. I mean, I don't have a calculator, so I tend to do things, I should collect some money and buy a calculator one day. Okay. All right, anyway, so, okay. Any other questions, concerns, comments at this point? Anything? Okay. Keep it simple. Okay. That's the most important thing. Okay. So chemistry wise, all you had to know here is what wave numbers mean. Wave number means 1 over wavelength. If you have that, then everything else is, something else. I have another hand. Oh, Carlos behind. Oh, okay. Depending on where you turn. Remember me name, say one more time.
Daniel.
Daniel, go ahead.
So what this is telling us is that, like, to answer the question, there's 12 kilojoules of energy per mole that is emitted at that
This is
or
absorbed.
absorbed at that IR
For CEO stretching.
for stretching.
Yeah, for CEO stretching, okay, to induce that transition, the energy of the radiation is 12 kilojoules per mole. That is the energy of the radiation. Energy of the
radiation.
photon, energy of one photon or energy of 1 mole of photon. That's all you're been told here.
Okay. All right. Thank you.
Wonderful. Any other questions, concerns, comments? Okay, so with that, we know how to calculate the energies from wave numbers at this point. Let's do something else now. I'll reopen this question. Yeah, why not? Anyway. Okay, I have reopened the question. So 1.98 is 2.0, right? If we anyway, that's something else. All right, one more question. Here we go. Here's an IR spectrum. How many CH bonds are present here? I'm trying to make a point with this activity. Hi, Lauren. That should be enough time for this question, I think. Okay. I'm going to close this question in 5, 4, 3, 2, and 1. Okay. So this should be a straightforward question. Okay. Either you might be using your fingers to count, or you don't have to count at all. Okay. Those are the two options. There's no middle ground here. Okay. So, before I look at your responses, I'm sorry, I had to do this. Okay. Now, remember, I made you write one sentence about IR spectra. What did I make you write? What did you write? Thank you. That is it. Period. Right? IR spectrum tells us what bonds we have in a molecule. That is it. It doesn't tell us how many. It tells us what bonds we have. Okay? That is all the IR spectrum can do. Therefore, the correct answer is not 2. It's this. Lucas, I'm come back. All right, I have reopened the question, okay? Lucas, what's up? Yeah. Yeah, all right, I'll elaborate a bit more. Okay. Now, now, so then one might ask, what about in the IR spectrum? Why do we see like 2 bands for CH? Okay, it only tells us the CH stretching wave number is different from the CH bending vibrational motion wave number. That is all that it tells us. Okay, so only thing we know based on the IR spectrum is in our molecule we have at least one CH bond, at least one. That is all we know. Okay, and then we have at least one OH bond and at least one CO bond, and that is all we get from this IR spectrum. Yeah. All right. What questions, concerns, comments do we have at this moment? Do you have a question? Yep. Everyone, right? Yes. Because it cannot. It just tells us that there are like CH stretching vibration, wave number is different from CH bending vibration. That is all it tells us. Yeah. A single CH bond can have stretching vibrations and bending vibrations. They will occur at different wave numbers. Abby, do you have another question? Danielle, you have another question?
So
Go ahead. I mean, chances are there are other people having the same. Go ahead. Throw it at me.
what can we determine from the peaks then?
That are that we have at least one CH bond, at least one OH bond, and one CO bond. That's all we can determine.
Okay, and then like we can see maybe that there's like 1, 2, 3 peaks in the CH, like labeled CH. Are we able to say anything about that?
No, nothing. We have at least one CH bond. Yeah. All right. So now here's another sentence I want you to write below what we wrote already. The sentence we wrote already. Okay. So I'm just giving you the idea, but you can write this in your own words. Okay. Um, if you do not see a bond, a particular bond in the IR spectrum, okay, then that bond shouldn't be there in the molecule. Okay. In other words, if you have a certain bond in the molecule, that will show up in the IR spectrum. There's no other way around. Okay. So one more time. Okay. So let's think about the negative thing. If you don't have a certain bond in the IR spectrum, then that bond has no business being in the molecule as well. Okay. So if it is in the molecule, it's on the IR spectrum. If it is in the IR spectrum, it is in the molecule. Every time. Okay. No ambiguity here. All right. Now, keeping that in mind, let's tackle the first question we were dealing with today to achieve the first learning objective. Go ahead.
Can I? So I need this dash here.
Oh, no, this is, I was just writing.
Oh, no, I understand. But,
Oh, no,
okay,
I know.
as long as you know it.
Yes.
Yeah. Is that your lunch? That's what my kids like too, actually, for some reason. All right. We have more than 90% responses here. So I'm going to close this in 5, 4, 3, 2, and 1. Okay. All right. Here's what I'm going to do. I'm going to show you the way I think about this because it's the first time we are doing a problem like this. And then I will look at your answers, okay? So usually, now at this point, we know that we have dealt with elemental analysis already. And then we have combined elemental analysis with mass spectrometry to determine the composition of the particle, meaning the molecular formula of the particles. Okay? So now what we're going to do is we're going to add IR spectra to this so that we can determine the structure as well. That's the third layer we're adding here. Now, the thing about the problem here, caveat here is this. All of these molecules have the same number of hydrogens, 4, same number of carbons, and same number of oxygens, 1 and 1, right? Therefore, the mass spectrum is useless, to put it bluntly, right? Okay, because everybody has the same mass. So only thing that matters to us here is the IR spectrum now. In the IR spectrum, we have OH bonds, CH bonds, and CO bonds. So if you look at the option 1, okay, we don't have CO bonds, we have C double bond though, which is not in our IR spectrum. Therefore, can 1 be our answer? No, this cannot be our answer because we do not have C double bond O in our IR spectrum. Therefore, it has no business being in our molecule. Okay. For the same reason, option 2 is out. And then in option 3, we have C double bond H. Do we have C double bond H in our IR spectrum? No. Therefore, option 3 is out as well. That means our answer must be option 4. Okay. And here we have CH bonds, these guys. We have OH bonds, these guys. And we have CO bonds, these guys. There you go. Done. That's all you have to do there. It's like solving a puzzle. They're fun to do. All right. What questions, concerns, comments do we have at this moment? Any questions, concerns, comments? We have a question? Wonderful. What's your name, sir?
Gavin.
This is
Hello.
Cam?
Gavin.
Gavin, go ahead.
What is the difference between the CH stretch and the CH bend? Like,
CH stretching is bonds going like this, stretching, right? Stretching. Bending is going like this.
So does the CH bend matter at all for making this?
Oh, I mean, you can say stretching doesn't matter. You can pick on bend. The
Okay.
only thing that matters to us is we have CH bonds there.
Okay.
All that matters to us. Yeah. Yeah. All right. Any other questions, concerns, comments? Okay. If that is the case, we have achieved our learning objective 1. At this point, I think most of us selected this answer, which is the correct answer as well. I'll reopen if in case somebody wants to revise the answers. All right. Learning objective 2. Then 3. Then we're done. Okay. Now, after analyzing thousands of IR spectra, the scientists have seen that these compounds over here represents the common bonding patterns of elements. Okay. What do I mean by common bonding patterns? I'll take an example. Let's take carbon, for example. If you take carbon in molecule 1, it's a methane molecule, by the way. Okay. How many bonds do we have around carbon? In the first molecule, how many bonds do we have around carbon? 4 bonds. Go to the next molecule with carbon. How many bonds do we have around carbon? Again 4. Go to carbon dioxide, which is the bottom, which at the bottom. Okay. How many bonds do we have around carbon? What's that? How many bonds do we have around carbon? Camilla? Carbon. How many bonds do we have? How many lines do we have around carbon? Do you see that? How many bonds? Camilla, do you see bonds? Like lines? How many lines do we have around carbon? Any carbon in this molecule? 4. So here's the question for you. What is the common bonding pattern of carbon? 4. There you go. So common bonding pattern is also same as the bonding capacity of the element. Here's what I want you to do. I want you to analyze these molecules and tell me the common bonding capacities of hydrogen, sulfur, nitrogen, phosphorus, chlorine, and so forth. Go ahead. All right. We are getting close to 90% responses. Okay, I think we have close to 90% responses now. Meaning I'm going to close this question in 5, 4, 3, 2, and 1. All right, and here are our responses. Okay, this is important. The common bonding capacity of carbon is 4, hydrogen 1, chlorine 1, fluorine 1, oxygen 2, nitrogen 3, phosphorus 3, and sulfur 2. Okay, now I want you to not memorize this, but know it. You have to know the common bonding capacities of the elements. Okay, any questions, concerns, comments? Is there a way? So, do you know how to know this without memorizing it? How? I'm asking. Like, is okay. So there's a difference between knowing and memorizing. Okay. So for an example, okay, I know Donald Trump. He doesn't know me, but anyway, I know it. I never memorize his name. Just like that. Can you know them? Yes. Yeah. Yeah. Are we okay with that? Okay. So this is important for your exam. Okay. Now Here's the trick I use to know them without memorizing. I'm serious. You need to know this for exam, okay? You will be tested on this. Now, how do I do it? To do that, let me jump a little bit to this beautiful table called periodic table. Now, I need your help to understand this, okay? Now, let's go to this rightmost column over here. Helium, neon, argon. Does anybody know what we call these elements? Come there again, I hear that. Noble gases? Yeah, thank you. Now, here's the question for you. How many bonds do they usually form? 0, right? Thank you. Oh, this is okay. These form 0 bonds. Move on over. Fluorine, chlorine, bromine. How many bonds? 1 bond. Move on over. Oxygen, sulfur, selenium. How many bonds? Everybody. 2. Thank you. Move on over. Nitrogen, phosphorus. How many bonds? 3. Move on over. Carbon, silicon. How many bonds? Oh, there you go. You don't have to memorize it. I'm going to give you a periodic table during the exam, okay? And if you have that, you should be able to tell me the bonding pattern or the bonding capacity of any element based on that. Deal? Deal? Yeah? Wonderful. No. So the question is, can we extend that? No. Okay? The reason is this. We are talking about the covalent compounds which are made by non-metallic elements. And where are the non-metallic elements? The top right corner of the periodic table contains the non-metallic elements. Okay? When you go to the left-hand side, they are becoming metallic. It is not relevant to them. Yeah? So you need to focus only on the top right corner of the periodic table when it comes to covalent compounds or molecular compounds. Yeah? All right. What questions, concerns, comments do we have at this point? Okay. That's our learning objective 2. We know how to determine the common bonding capacities of any element in a covalent compound. Yes? Yeah? Okay. Now let's have some fun with this now that we know how to do this. Let's try. Let's try this question. Here we go. So let's say that you have a covalent compound made between nitrogen and chlorine. Can you determine the molecular formula for that? So when I walked around, Zach asked me a question about hydrogen. So hydrogen is not any of those groups, okay? So here's what you need to know, okay? Hydrogen always form one bond. Always from one bond, unless you are from ASU. In ASU, everything is possible, right? Okay. Or you are taking advanced inorganic chemistry courses where you talk about bridging hydrogens. Okay. But hydrogen, the common bonding capacity is 1 always. Three. All right, we have more than 90% responses now. I'm going to close this question in 5, 4, 3, 2, and 1. And yeah, so the correct answer is NCl3. Why? In NCl3, we have nitrogen. We have 3 bonds for nitrogen and then 1 bond for chlorine. There should be something like this. All right. What questions, concerns, comments do we have? Any questions, concerns, comments? You have a question, sir? Can I do you have a microphone here? Yeah. Remember me name, sir?
Pierce.
Yes, yes.
Does the order of which you like write the elements?
Yeah. So, okay. How do I answer this? All right. Right. The question is, does the order matter? So to answer that question, we need a little bit more information than we have now. So a direct answer would be usually when we write a compound, the more electronegative atom is written last. Okay, so between nitrogen and chlorine is more electronegative. That's why it is written like that. But we don't have that information now because we haven't talked about that information yet. Yeah, but I don't know how else to do it at this point rather than that. Yeah. Okay. All right. Any other questions, concerns, comments? All right. Don't worry about the electronegativity plays. Okay. We'll talk about that in about 3-4 weeks after your next exam. Okay. So not yet. So with that, now we are done with 2 learning objectives. Okay. Moving on to the last one. So actually the last one is a preview of coming attractions mainly. So what we're going to do now is we know the common bonding patterns of all elements. We want to be able to explain this. Now, whenever we are explaining something, what do? How do we explain? How do scientists explain things? They use what? Okay, oh yeah, they use that when they solve problems. But when they're explaining, what are they using? To explain something? Models. Thank you. We use models, right? Like the particulate model of matter, the ideal gas model. Okay, just like that, we'll be using a model to explain this. Okay. Now, to understand that, we are going to be looking at a little bit more data now. More specifically, we'll be looking into the atoms and then we'll talk about 2 types of data: atomic radius and the ionization energies. Okay, we will understand what is meant by that. We'll start today, but we will complete this discussion on Thursday. So when it comes to atomic radius, it's about the size of the atom, right? So now let me remind us. When it comes to atomic radius, if you can remember our discussion about the atom, if you compare the atom to a football stadium, okay, the nucleus is like the football at the center of the stadium. The rest of the space is determined by the electron cloud. So you would have to keep in mind it is the electron cloud that determines the size or the radius of the atom. Okay, so electron cloud is the key when it comes to the size or the radius of the atom. And then how do we get this information? We get this information through X-ray crystallography. But that doesn't matter to us because I'm not going to ask you any questions about how X-ray crystallography works or anything like that. Okay. So anyway, so let's think about some atomic radii data. And then before I show you this question, I want to make sure that you understand some jargon that we'll be using. That is, in a periodic table, we have groups and we have periods. I want you to know the difference between the groups and the periods. Okay, so if I talk about going down like this, down a column like this, or up on a column like this, what do you call these columns? Are they groups or are they periods? Okay, these are groups. Okay, so the columns in the periodic table are called groups. So like noble gas group, okay, the halogen group, and so forth. Okay, so we have groups. These are the vertical lines or the vertical columns in the periodic table. On the other hand, we have periods. So periods are going from left to right or right to left. Okay, those are these rows in the periodic table. Okay, these are called periods. So this is the first period, second period, third period, fourth period, and fifth, and so forth. Okay, it goes like that. Do we have any questions about the difference between the groups and the periods at this point? Okay. All right. Now that we got that out of our way, we know the difference between groups and periods. What I want you to do is answer these questions, okay? I am showing you some data. On the y-axis, I have the atomic radius, and on the x-axis, I have the atomic number. Based on this information, based on this data, I just want you to make some observations here. How does the atomic radius change across the period, and how does the atomic radius change going down a group? Go ahead. I just want you to make some observations here. That's all I'm asking you to do. Can we talk with them? I'm gonna tell you the answer already. Can you talk? So what? So between from going from lithium to neon, what do you notice to the size?
But
No, forget about that. Look at the data. Lithium to neon. What is happening to the size? That is it. That's all I'm asking you to do. You don't overthink it. Yeah. All right. So that should be enough time for this problem. Do not overthink this, okay? I'm not asking you to explain anything. I'm not asking you to draw conclusions. I am just asking you to make an observation. Tell me what is happening. Okay, across the period, what is happening? Going down a group, what is happening? That's all I'm asking. Do not overthink this. Yeah? Okay. Now we have more than almost 90%. All right, I'll give you 10 more seconds. Please submit your answers. All right, I think we have more than 90% responses now. The question will be closed in 5 seconds, so please submit your answers. 1 second. Okay. All right. Let's see your responses, okay? So most of you observed that atomic radius decreases across the period, okay? If you did not see this, let me help you see this trend. Now, if you look at periodic table, let me go back to, where's my periodic table? Okay. You see that lithium to neon is one period. Hydrogen to helium is one period. Lithium to neon, sodium to argon, potassium to krypton. Okay. So those are our periods. Now, if you go back to the question one more time. Okay. So first period, hydrogen to helium. What has happened to the size? The size has decreased or increased? Everybody, please, I need your help here. When you go from hydrogen to helium, what has happened to the size of the atom? Has it increased or decreased? I cannot hear you. Decreased, right? Do you see that? So here's the atomic radius. It's going down. Like it starts here, it goes down. Next period starts from lithium, right? Lithium to neon. What has happened to the size? It has in general decreased. Next period, sodium to argon. What has happened to the size again? Decrease. Potassium to krypton again, decrease. So across the period, size of the atom decreases. Yes? Yeah? Any questions about that? That's the first observation. Okay. Now, groups. Now, what are groups again? Let's actually, look at some of these groups. So, in the first group, we have hydrogen, lithium, sodium, and so forth. Then beryllium, magnesium, and then helium, neon. Okay, those are our groups. So let's look at this first group over here because it's easier to see in the question itself, right? So let me start the question one more time, clear my doodling. Okay, So lithium, sodium, potassium, they are in the same group. So when you go down from lithium to sodium to potassium, what is happening to the size? What is happening to the size when you go down the group? It is increasing. These are just observations. Okay, you are given the size data. You see that when you go from lithium to sodium to potassium, size is increasing, meaning when you go down the group, size is increasing. That is it. Any questions, concerns, comments? Okay, now here's the real thing now. Explain it. Go ahead, I'll give you a minute. How can we explain this? All right. Now, we know whenever we are asked to explain something, we are using a model. That's what we do as scientists, okay? So here's the model we can use to explain this. We call this the shell model of the atom, or atomic shell model, okay, whatever, okay? Now, here's how it goes. The electrons in atoms are filled to shells. Okay, so the first period has only one shell. Okay, so we only have two atoms there as well. So those electrons are filled to the same shell. But when you go from hydrogen to helium, you have more protons in the nucleus of helium compared to hydrogen. Therefore, those electrons are attracted more towards the helium nucleus than the hydrogen nucleus. That's why we have a small electron cloud in helium compared to hydrogen. Now, let's move on to the second shell or the second period. Okay, in second period, we have two shells. The first shell, which is the filled shell, where we have which we have up to helium, and then the third electron is filled to the second shell. Okay, and the fourth, fifth, sixth, seventh, eighth, ninth, 10th. Okay, so they are filled to the same shell, but we know when you go across the period, you are increasing the number of protons in the nucleus. You are increasing the atomic number, meaning the number of protons or the positive charge of the nucleus increases. If you have a greater positive charge, that's going to have strong attraction towards the electrons. As a result of that, these electron clouds gets closer to the nucleus, meaning your atom is going to become smaller. Okay. Now, when you go from 10th to the 11th electron, that 11th electron is not filled to the same shell, because if it did, it should be the smallest. Okay. Instead, you can see that sodium is much larger than any of the other atoms here. The reason is the 11th electron is not filled to the same shell. It is filled to a new shell, the third shell, which is larger than the previous shell. So each subsequent shell is larger than the previous shell, and that's why when you go down a group, the size of the atom increases, because each added shell is larger than the previous one. Okay, and across the group, because the electrons are filled to the same shell, but the atoms have more protons, they're going to have strong attraction towards the electrons, and that's why the atomic size decreases across the period. All right, I explained the trends using the shell model. Now I want you to think about this, talk with your neighbors, okay? And then, you can ask anything like, what the heck was that, right? Anyway, okay, something like that. And then anyway, write your explanation in your own words. Go ahead, and then I'll check back with you. Let's do that, yeah? All right. All right. What questions, concerns, comments do we have? Any questions, concerns, comments? Anything? Okay. So I'll do one other example and then I'll move on. Okay. So for an example, okay, oxygen, let's say fluorine. Let's say fluorine, okay? Fluorine is smaller than oxygen. If somebody twisted your arm and asked you to explain this, what would you do? You need to mention two things, okay? The electrons are filled with the second shell in both cases. In oxygen and fluorine, electrons are filled to the same shell. However, fluorine has more protons in its nucleus, meaning you have stronger attraction towards the electrons by the fluorine nucleus. As a result of that, electrons are getting closer to the nucleus in fluorine, meaning you have a small electron cloud in fluorine compared to oxygen. And that's why fluorine is smaller than oxygen. So that should be the thinking or the words that should go into explaining why, fluorine is smaller than oxygen, or why carbon is smaller than boron, and so forth. Okay. And if somebody asks you why sodium is bigger than lithium, okay, what would you say? Sodium has more shells. More shells means each added shell is larger than the previous one. Therefore, sodium must be bigger than lithium. That is it. That's easy. When you go down the group, it's much easier. All right. Any questions, concerns, comments at this point? Okay. So let's do this last question. This is this is the second period elements. I want you to arrange them from smallest at the top. No, give me a second. Largest at the top and smallest at the bottom. Go ahead.